yeah. So thank you so much, my dear friends. I'm trying to guess your name. It doesn't say. Okay, I'm gonna guess in a few minutes. All right, so now that's week 4. All right, so if your Wi-Fi is bad, don't open your camera. Priscilla, it's okay, we're human. I would love to see your stress. Give it to me. I'm also stressed. Everybody is. So yeah, it's okay. So this is the plan for week 4. And as you know, you are ahead of the Tuesday section. That's why I'm writing those, just to be able to follow with them the same plan. I would just want to say that lab 1, you should receive the corrections today. Please check the comment section, because I'm going to write everything on the comment section, not directly on your lab report for many reasons. Usually I correct on the lab report because for the partners, it would be easier for me to copy paste the same comments. For example, I had Yara and Ali. I wrote some comments for Yara and the same for Ali because it's the same lab report. Same for Noha and Layla. If I would want to comment directly on the lab report, it will be difficult for me. The best way would say, Ali, go check the comments on Yara's lab report. And I suppose this is not fair because at some point, you would be separated with some reason, you know? What if Yara will not give the comments to Ali for a reason? So this is the best way for me to be able to communicate within partners. If you have questions, please let me know. Yes, Yara, معك حق ما تحكي معه. ثقيل علي. So lab 2, I heard that you still have a lot of questions. Again, lab 2 is about motion on an incline. I'm gonna open lab 2 now. And question number 1 I've been asked was how to find the propagation of error when I have mu to be tangent theta. By the way, be careful. Oh, it's already open. Be careful when you have the error on an angle in degrees, convert it to radians, because degrees is not an appropriate unit to keep. I can explain more if you want me to. All right, anyway, let me start with the question that somebody asked me a few minutes ago on the email. All right, so we know for a fact that mu, the coefficient of static friction, is equal to tangent theta, okay? I can see probably my internet is weak because my pen is slow. You have the error on theta, and the question is find the error on mu s. So the best way is to say the error on mu s is equal to the derivative of mu s, derivative of mu with respect to theta, okay, times the error on theta. I'm not gonna say squared and square root because it's gonna neutralize each other. Now, how do I find the derivative for tangent theta? I totally forgot. Is it 1 over cosine squared? What is tangent theta? Yeah, for the students who already Googled this. I did not do that for a long time. I forgot.
I did, doctor. It's 1 over cosine square.
Yeah, so 1 over cosine squared. I'm sorry for my pen. So cosine squared theta, all right? And then the error on theta, you already know it. It's half a degree if I'm not wrong. Change it to radians because degrees alone, like under the cosine, no problem. But alone, it's not an appropriate unit to keep. By the way, be careful while you do cosine squared. It's cosine theta times cosine theta or cosine theta with parentheses, all of it squared, because a lot of students don't know how to use the calculator on that level, and it's okay. Do you have any questions concerning that? I suppose not. Concerning A theoretical, did you manage to find the uncertainty on A? Because A is G sine theta and you have to do the propagation of error as well. All right, anybody has a question concerning this lab? Please speak up. No one?
Doctor, I didn't get the question number 8. But you exactly what want us to do in 8 and then 5.
All right. Priscilla, please call me Jessie. If you cannot, Miss Jessie would be okay. So, okay. 8, slowly incline the track from the horizontal surface. This part of the experiment is not in my video. That's why I shared Dr. Summer's video, definitely after telling her, because I did this experiment for Physics 111 and they don't have this section. And now, you know, we cannot go to the campus anymore. So what Dr. Summer did, she was actually lifting the angle slowly, waiting for the angle at which the box will start sliding down the incline, and she would manage to take the angle. She did 5 trials. It's just the same exact experiment repeating it, just to increase the precision. So she was finding theta, and theta is the angle at which the box would start sliding. That's why it would give me mu static, which is the threshold at which motion will actually start. She did the experiment on the wooden surface, and then she repeated on the textile surface, and this is how the box is. And you had this part was wooden and this part was textile. By the way, the same surface, like she used this side and this side, same area of the surface, and she got different thetas and different mu's. For the textile, probably it's gonna be less friction or more friction. You can tell from you. That's it. Did I answer your question, Priscilla?
Yes. So the values given are actually the values of mu, and you have to find the mean and then the uncertainty, right?
Actually, she was measuring theta, and then you do the average for theta, and from the average you find mu.
Okay.
And therefore, the uncertainty on theta would be the RMS value, since we're doing the average. Do they mention in the procedure they want you to calculate the average? It should be somewhere. Let me see. Repeat several times, then find mu. They don't say average, but assuming many trials to find the average. Okay, and for number 5, Priscilla, they say devise a procedure that could verify. So from number 4, I suppose you noticed that the acceleration, which is g sine theta, is not mass dependent. Not mass dependent. And number 5, you have to come up with an experiment of your own. For example, on a horizontal track, something free fall, pulley, something wire, tension, anything where acceleration would be mass dependent.
Okay.
Because F equals ma, it is mass dependent. It's only not mass dependent in this case because the force of gravity is involved, which is mg or mg sine theta, and that's why m would cancel out. Just think of any experiment where you have other forces other than the mg. All right. Devise a procedure would be just briefly say what equipment you need and how the setup look like. You can have a sketch and a pencil to show how the setup is, and explain how applying Newton's second law will show you that A is mass dependent and what to measure. What to vary if you want. Okay. All right. I can see somebody's raising hand. Yes, Jane?
Yes, doctor. I just wanted to ask, there's one question where I thought it would be better to include a diagram because to better explain my analysis in order for...
Of course.
But my question is هلا هيدي الدايجرام I found it on a website do you want me to cite it or would you rather have me scan it draw it myself?
Don't waste your time. Take it and cite it. Of course.
Okay, perfect.
Imagine you're doing the work while you can find something nice.
Okay,
am I doing the same in my presentations? Yes, I am. All the pictures I'm taking from everywhere, and some of which I'm not citing because but probably I should. So yes, use any picture you want and use it to explain and draw anything you want. All right. By the way, so far I'm impressed with your lab reports. I was expecting, I don't want to say worse, but I was expecting probably students, really beginners on that level, and you're doing okay. All right, let me check the questions in the chat. Can we postpone? Layla, what do you mean by postponed? You need more time? Isn't the deadline Tuesday evening? Let me know, Layla, what's the problem? All right, in question 6 and 7, do we directly write the expression or do you want to see the derivation? And number 6, if you take the force of friction, do the derivations. This is what they want. Yeah, and for number 7 as well. However, for number 7, I showed you how to start in our previous live session. How to find the error on G and sine theta? We didn't get, okay. All right. Layla, how much time do you need more? Like 1 extra day or few hours?
Doctor, probably 1 extra day.
Okay, Layla, Personally, I don't mind, but be careful because we're gonna start lab 3 and the deadline is gonna be next Monday. It will be a lot for you to handle.
Yes,
So
of course,
the sooner
I
the
know that.
better, because we cannot push the experiments over the weeks. We only have 12 weeks per semester and we have 10 experiments to finish. Talk to me privately and let me come up with you with a very specific deadline, okay? I
Okay,
wanted to
doctor,
say
thank you.
something concerning G and sine theta. Yes, let me write it down here. So we know that A is equal to G sine theta, right? And for you to do the propagation of error, my pen is very slow. It's from Zoom, I think. We need the error on theta, and it's here. And we need the error on G, okay? And I promised to give it to you, and I did not. I forgot, actually. And I remained silent for a week. I thought probably you would want to ask me. Anyway, probably you can say 9.8 plus or minus 0.1 meter per second squared, or 9.81 plus or minus 0.01 meter per second squared. I don't have any mean to measure G, so I'm assuming, which is not wrong, by the way, okay? The reason why I'm doing that is only to push you practice more propagation of error. Do I have the right to do this? No. It's only to push you more through propagation of error. You see what I mean? So yes. Now, a lot of students already finished from this part. So whatever you did, keep it as such. And for the students who still did not do this part and they need a value for G, take it 9.8 plus or minus 0.1. Why not? Okay. Yes, there's nothing on Blackboard that would not let you submit beyond 11 p.m. 11 p.m. is only an agreement between us. It's not an exam. It's only an agreement between us for me to help you and give you a structure. But let's say you submit 11:15, Blackboard will not say anything about it. Blackboard will not know. Okay? Probably I can tell only the time of the submission, and which will be not a big deal, okay? But however, if we are doing an exam, it's going to be different. So now only for the lab reports, the 11 p.m. is flexible, okay? If I prove an equation in the previous, yeah, you can. You don't have to prove it again. Of course, you can do that. The error on theta is the same as sine theta. No, you basically need to do the derivative of A with respect to G and the derivative of A with respect to theta. And the derivative of sine theta is cosine theta, and then you multiply by the error on theta. So here you cannot use the chemistry propagation of error anymore because you need to do the derivative of sine theta, okay? So no, the error on theta is not the same as error on sine theta. I took 0.01, okay, no problem, Jane. Do we always consider theta and radius in finding the uncertainty? So basically, when you say alpha theta, and alpha theta is not under any function like sine, cosine, or tangent, it's alone. Yes, do not use degrees, always use radians, not only in uncertainties. Let's say you want to find the area of a certain part of a circle, of a disk, like your pizza slice. You do theta times the radius, and here theta must be in radians too, otherwise the equation of the area of a disk will not work anymore, you see? So theta in any equation must be in radians if it's alone. If it's under sine or cosine, it doesn't matter because sine and cosine would remove the unit. All right, that's it. Imad has a question, go ahead.
Yes, doctor, بس عندي a small question. بس بدي ليه أنا الأير تبع الأفريج أنا عادي بعمل standard deviation صح؟
Divided by radical n.
Yes, of course.
Okay. So again, many science labs for error on an average, they do standard deviations, and many other science labs, they do the alpha RMS. And they're actually very related, okay? The difference is the standard deviation, you know how to do it, and the RMS is the standard deviation divided by radical n. I asked someone in the field to see why different scientists are doing different things and which one is right. So basically, I got an answer which is, it doesn't actually matter. It depends on how big your system is. I don't know what they mean. I'm not a statistic person myself. I know all physicists, this is what they do. And it's not a big deal, basically. So I'm trying to tell you what you're learning in chemistry is not wrong or different to what you're learning in physics. It's just a way to approach things. And eventually what we need to know is how big the scattering is. You see, I don't know if I convinced you, but I thought you need to know this. All right, if you guys, Ahmad, do you still have any question? Your hand is still up. Fadi, go ahead. Yes, Fadi, your question.
Yeah, I wanted to ask about question 8, which you clarified. And question 1, why should we find the uncertainty of the acceleration collected? We're going to use the standard deviation for the average?
All right, for the average, you will find the error on the experimental acceleration. But for the theoretical acceleration, it's different, isn't it? To calculate the theory, you do g sine theta, and the uncertainty is due to the uncertainty on g and uncertainty on theta. For the average, you do the 5 different trials and you see how scattered they are. So the RMS is only on the experimental. So here we're doing a experimental and a theoretical, and they're not related, right?
Okay, but for the acceleration values collected above, there's we don't include an uncertainty through the calculation.
You mean uncertainty for each?
Yeah.
What made you think that? Did you see a previous lab report?
No.
All right. So basically in the past, students, all right. So my answer is no, you don't need to include any uncertainty for each trial. I was surprised by your question because I gave you the results acceleration only with no uncertainty on these. Yeah, I want you to be careful if you ever look at previous lab reports. The procedure is actually changing and sometimes you will get confused. I'm not saying it's wrong to look. Of course, you can look anything you want, anywhere you want. And you can also ask, why did we used to do this in the past? Why is this different than this? And be careful, read the questions again, because sometimes the question might be different. So to answer your question, Fadi, you are given the acceleration for each trial. Your job is to only do the average and find the uncertainty on the average. Okay, did I answer your question?
Yeah, and I have a question regarding question 8, if that's fine.
Yeah, of course.
And question 8, the propagation for tan theta. Tan theta, the uncertainty is on theta only. So how can we use the derivative of tan theta to find the uncertainty?
All right, so you basically say the error on mu is the derivative of mu with respect to theta times alpha theta, done. And the derivative is actually this guy. That's it. So by doing the derivative, you simply have to multiply by the error on theta. Yes?
Okay, yeah, I got it.
All right, cool.
Thank you.
Any more questions? If you guys are done, we can say that we're done with item 1 and item 2. All right. I need us to do linear regression. Even if we won't have the time to do 3 and 4, it's okay. I can sacrifice 3 and 4, although I don't have to because it's really simple and quick. But okay, so this is item 3, this is item 4, this is item 5. I'm sorry for that. I think and I believe linear regression is very important, and we need to take our time to do this today, and we cannot postpone it anymore. Okay? So I'm gonna go to data analysis part 2. This is the thing that I was postponing since forever. I will try my best to be not so brief and not so detailed. Please stop me if you believe I'm missing something. All right, the content, and that was supposed to be covered during week 1. Okay. Why is a graph a good communication tool? Why linear relationships? How do we calculate the slope? Why do we calculate the slope? And how do we find the error on the slope? Did you ever do that before?
The errors of a slope?
Yeah. All right.
Isn't it maximum gradient minus minimum gradient?
Yeah, you can do that in high school. it's a good way to approach things. Although we're not gonna use this method, we're gonna use something more, I'm gonna say advanced, okay? So I'm gonna suppose that you know nothing about that, okay? I'm gonna go over the first item very quickly because we don't need to take our time. In this section, I was discussing different types of graphs. I was saying that a graph is a very important communication tool. It's very important to show a title, to label your axis, both axes, to show a unit. And every time you have many plots on the same plot, try to explain through a paragraph or try to show a legend explaining what each color or shape represent, okay? I'm gonna show you, I was planning to show you some graphs, some of which are not good communication tools, some of which does not show an appropriate legend, some of which do not show an appropriate unit, and so on. For example, this one looks so cool, but I don't see any unit for the x-axis. I don't understand the y-axis, which is okay. I see a good labeling, like the legend. I don't see a title, you know? And how about I continue here? No label for the y-axis, for the x-axis. The title is bar charts. It means nothing to me. All right, it has a legend. I don't know what it means though. Although it looks very pretty, but it's not a good communication tool. So the point behind item 1, make sure to include a title, make sure you label your axis, make sure you have units, make sure you show your actual measurements. And then if you want to show a trend like a line or something, you can do that, but do not remove the points, the actual measurements. Make sure to show a legend that is clear and visible, okay? You need to learn how to do that on Excel. I can see so far that you're doing okay. If you need help, YouTube can help, Jessie can help. And it's okay if you waste some time during the first few weeks because you will learn to do that over the whole semester, okay? Now, why linear relationships? Sometimes when we do a plot, we get a scattering. The scattering would mean a linear relationship, like both parameters affecting each other in a linear way. And sometimes it's not linear, like in this case. So be careful, it's not always linear. If you go to Excel, and probably I need to show you at this point because you've never done this before, you can display the equation. Let me show you here. You can display the equation of the straight line. Okay, by the way, here they're plotting t squared versus L. And there's an r squared coefficient that should be very close to 1. If r squared is very close to 1, it means it's superlinear. So 0.99 shows that you have a linear relationship. It's not 1 because you have some scattering. Do you see this point? Do you see this point? So those are sources of errors, and it's okay. Remember, we have real setups, not ideal setups, you know, like this is reality. This will not give you a straight line. This is not a linear relationship. By the way, this is the period of a simple pendulum. If you remember well from high school, T is equal to 2 pi radical L over G. And obviously you see T and L are not proportional. So if you plot T versus L, you will not get a linear relationship. However, if you plot T squared versus L, you do get a linear relationship. So if I find r squared, the r squared function here, it will not be close to 1 because obviously this is not a straight line. Okay, you see the curve. Okay, in a minute, probably I should show you how to do it on Excel. This is another example of a linear relationship that shows the equation of a straight line. You see the slope and the y-intercept? Yes. And this is another example where they show you the equation of the straight line with the r squared function. 0.989, 0.855. So the scattering is huge. And here, what do you have? 0.96. You see the scattering? And here the scattering is less 0.99. So it's a good thing to see. And you will be given the equation of a straight line. This is not a linear relationship. Okay, this looks like a parabola, and one of the students decided to do the linear fit. And they got an r squared function or an r function that is way far from 1 or 0.9. Obviously, because this is not a linear relationship. So not any set of values would give you a linear relationship. okay? Sometimes it's obvious. Now let me go to my Excel and show you quickly how to do it. By the way, you can find the slope and the y-intercept using your calculators. Since everybody has Excel, how about I don't teach you how to use your calculator? However, I would want to upload a YouTube video done by myself many months ago on how to use the calculator to find the slope, just in case you want to learn, okay? So I'm gonna open a new folder on our Blackboard called Data Analysis Part 2, in which I'm gonna put all the links you need, okay? Now I'm gonna put X and Y. Let me make this a bit bigger and let me make it centered so you can see. X and Y are not needed. They're only for myself because I need to remember which is the X, which is the Y. I'm gonna throw values randomly and I'm gonna say this is the double, although experimentally we will never ever have this. Usually we have a scattering around some linear relationship. Are we allowed the TI calculator? Of course you are allowed this, Jane. If we're gonna be online, I won't even be able to see your calculator to reset it, and it doesn't matter because you can easily put any equation you want next to you. So all the exams are gonna be open book in a way, okay? So yes, you can use your calculator, and yes, you can use Excel, and even if we go to campus, the exam is gonna be computer based. So you're gonna go to campus and you're gonna have your computer on you, and you're gonna sign into Blackboard and do the exam online while you are on campus. All right, so get ready for that and train yourself to use your calculator, to use Excel, anything you want, okay? And the more apps we use, I believe, the better, because we will have the chance to think and analyze our data better and not waste time doing the work on hand, you know? So you're supposed to select the values only without the X and Y. Insert, I'm sure there's many other method. This is how I do it myself. Probably you know how to do it faster. I take scatter without any line, okay? And then I do right click, add the trend line. I know some different versions of Excel which show you things differently, but it's basically similar in a way. I'm gonna pick linear, not exponential, not logarithmic. I'm gonna pick linear. I would say display equation and display R squared value, okay? So here you can see, by the way, it's not very visible, but I can easily select the whole thing. Just a second, select the whole thing. No, select the inside, and make it bigger so you guys can see it. Bold. So the equation of a straight line here is yx equal to 2x, obviously, because I picked my values like that. And the R squared function is 1 because it's super linear, superb, because I did times 2. But you know, experimentally, you will not get this. For example, if this is 2.1, and this is 8.2, and this is 9.9, and this is, I don't know, 13, things are gonna change a bit. Let me change even more, 0.8, and this is 3.3, and this, okay, things are changing, but not the equation. Why? 5.8. Okay, let me remove the equation and put it again. All right, can I now add a trend line, format the trend line, and display equation, display R. Okay, I was hoping the equation is gonna change directly, because in the past I thought it would change. Anyway, you see, all the scattering I induced on my values created an R squared function far from 1, but it's still okay because it's close to 1. And you can see the slope and the y-intercept, okay? This is key. I'm gonna now go back to my presentation, even though I still want to discuss many other things, but it's okay. All right, now how do we find the slope? Calculate the slope. Please do not use this method, all right, that states y2 minus y1 over x2 minus x1. This method is only used if you already have the line and you can pick 2 points on the line. But in your case, you only have the points and you don't know where the line is. And if I ever do a best fit line, it will eventually be like the average line, and it's gonna pass through the points, not on the points, like in between the points, which means I don't know which points will belong to the line. So please do not pick this unless you have the line, okay? Some students will always do this method. Don't do that. Excel will give you the straight line, will give you the best fit. All right, how do we calculate the slope using Excel? I already showed you. Insert, like select first, insert scatter. And this is an example where it shows you the equation and the R squared function. Using the calculator, there's a video you can watch. And I wanted you to try this out, all right? If you want, we can discuss it tomorrow. Not tomorrow, next time I see you. I'm not planning to give you extra assignments. How about we don't do this? We skip it simply. And since we have lab 3, we can apply this directly on lab 3. Lab 3 is not as easy as this one though, but it's okay. Now item 4, what is the slope needed for? Okay, like for example, if you do F equals MA, and probably here I can ask somebody like Jane. Jane, what do you think we can plot in this case to get a linear relationship? Just pick any example.
What do you mean, doctor? I didn't understand the question.
All right, so let's say I measure A for every force applied. If I ever plot F versus A, do I get a linear relationship?
No. Yes, you do, actually, you do.
If I plot A versus F, do I get a linear relationship?
Yes. No. Yes.
Yes. If I have a constant force, I'm varying the m and having different acceleration, and I decided to plot m versus a, do I get a linear relationship?
If we have a constant?
Yes, if f is a constant. Because
yes, we do.
Actually, no, because m and a are not proportional, they're inversely proportional, and you get a hyperbola.
But what if there's a constant?
Even if your y is a constant, y is equal to constant over x. It does give you a hyperbola, even though you have a constant.
Oh, yeah.
So the constant
yeah,
was
you're right.
Stay with me, Jane. Jane, what will the slope represent in this case?
F over A, the mass.
The mass. And in the graph below? The slope
one
is?
sec. E over F. 1 over the mass.
Yes, thank you, Ellie, for your answer. So basically, this is why we need the slope. Once we calculate the slope, we can deduce m or 1 over m or any other constant in my problem. I'm gonna do this and this after reading Priscilla. You didn't explain how we should find the slope, or I missed out something. So how do you find the slope? If I go to my Excel, the slope is 2.1. So by simply writing the equation of the straight line, I can read the slope directly. Or simply go to the video of how to find the slope using a calculator and learn how to do it. Although if you have Excel, I believe Excel is faster. Okay, so just read it from your equation. Now I can ask Ellie. Ellie, can you help me with this one? Ohm's law. All right, so let's see.
Hi, yes.
Yes. So let's say, what will you plot to get a linear relationship? Give me 2 examples.
Let's plot Q against I.
And what will be the slope then?
The resistance.
The resistance. And any other example?
You can plot I against U.
And what would be the slope?
1 over resistance.
And what happens if you plot R versus I?
It's a parabola, I guess.
Hyperbola, you mean? Yes, it's not gonna be.
Yeah.
Thank you so much, Priscilla. For this equation, T is equal to 2 pi radical L over G. If you plot T versus L, do you get a linear relationship?
No, because they're not directly proportional.
Okay, what will you plot to get a linear relationship?
T squared versus L.
Any other example you can think of?
إذا عملنا L versus T squared.
Okay, any other example you would think of? Probably T
1 over G, yes.
Versus radical L.
True.
Would work.
Yes, T.
All right. In this case, Priscilla, T squared versus L, what would be the slope?
لحظة شوي إذا عملنا I think 2 pi over G.
or
No.
4 pi squared, because you're gonna square both sides. So 4 pi squared per g. Okay.
Yes.
So if you're not being able to see it, this equation can be written. I need a smaller pen. This equation can be written as t squared. I'm gonna square both sides to be 4 pi squared into L over G. So by simply plotting, my blue pen again, plotting t squared versus L, the slope is the remaining, so 4 pi squared over G is the slope. Okay, you were very close. And I need to tell you something, my dear friends, you are very bright. I'm so proud of you. This was so difficult for other sections in the past. I always thought that the generation of COVID, of online teaching, are not doing well. And look at you, you're proving me wrong. Yes, I'm glad. I hope so. All right, now, anyway, probably you would have gaps in the future. Just let me know, okay? So error on the slope. Now, whatever, you see the scattering we have around our straight line. So obviously here, I'm gonna find an error. This is very similar to finding an average. Isn't the red line an average? And the scattering, doesn't it show something like a standard deviation? Now I'm gonna do exactly the same exact thing, but two-dimensional. So I'm gonna find the RMS two-dimensional, and I'm gonna call it the error on the slope. How do I do it? I'm gonna look for the vertical deviation. Do you remember in the alpha RMS, you had a term called deviation, di, sigma di squared, and the deviation was actually m1 minus m bar, right? Here I'm gonna do the y, the ordinate of the point, and the ordinate of the blue line, and find the difference. I'm gonna call it deviation as well. So I'm gonna look for all the vertical deviations, some of which are positive, some of which will be negative. I'm gonna square each and add them up exactly like I did in the RMS. How do I find the deviation? I'm gonna take y1, which is the ordinate of this point, and I'm gonna take minus, I'm gonna take the equation of the line, so bx1 plus a. Okay, so this part, and let me change my pen, this will give me the equation of the straight line. So this is the y of the straight line, and this is the y of the point, and I'm going to find the difference. I want you please to forgive me for writing bx plus a and not ax plus b. It's only because Japanese Casio calculators would use bx plus a instead of ax plus b, and I want to take it as a habit, okay? It's not just to torture you. And you can see here the deviation is less, is much smaller. You see? So definitely the error on the slope here will be smaller. Here they're showing the vertical deviation, y and y, and square it, find the sum. And my purpose is I want this to be minimum. So the choice, Excel would choose the best fit line following this strategy, the deviation to be the minimum, okay? But you don't do any work like that. Excel will do it for you. All right, so now you're gonna use this equation. I don't want to demonstrate it for a long time. I will give you another video, and I'm really sorry for that, but I'm talking about very short videos in which I explain how to find the error on the slope. But I'm gonna go over it now a bit. N is the number of points. This is the error on the slope squared. So when you're done, make sure you do radical the answer and make sure to round to 1/6 to add a unit, and to round the slope accordingly. It's a regular uncertainty. So again, N is the number of points. What is EI? EI, I'm gonna write E1, I already wrote it. E1 is Y1 minus the equation of the line, which is bx1 plus a. Supposedly you already found b and a before you do the error. B is the slope and A is the y-intercept. So you find E1, E2, E3. I'm not gonna give you a lot of points, probably 5 points on the graph, up to E5. So you do squared for each, then you add them. Now what is delta? Delta is n into this. So if I need to expand this one, this is x1 squared plus x2 squared, and then you add them up, And this one is different. This, you do x1 plus x2, and eventually you square the whole thing. Okay, x2, and eventually you square the whole thing. Okay, fine. And you plug in everything in here. And probably I can go back to this one again next week because you need time to grasp this one. I also included something called the Linus method. I want you to look more into the Linus method and probably include that in our weekly plan for next week. The Linus method would give you, it's a function on Excel that would give you the slope, the y-intercept, and the error on each very quickly. All right, if you learn how to do it, probably you won't have to use this equation anymore. Okay, fine. I did not quite understand the basic of this error equation, the basis. Anthony, can you please speak up? What do you mean? You mean like when do we use this?
Oh, basically, how did we derive this error equation? Out of what?
All right, so probably I can show you here, although it's gonna be time consuming. So what I do here, let's say I just found out the slope to be 2.1, right?
Yes.
And I need to find the error on 2.1 because I can see some scattering in here. So probably there's an error. So I'm gonna use this equation. What is the number n? I'm gonna look here. I have 1, 2, 3, 4, 5 values. So n is equal to 5. I'm gonna compute E1, E2, E3, E4, or 5, which is the deviation for each point. I'm gonna find the error, like I'm gonna square each, add them up. Then I'm gonna find delta, which means I'm gonna take all the x points, like the abscissa of each point, square each, add them up. This is a way to find the error on the slope. So do you remember when somebody told me from your class that to find the error on a slope, I draw the best fit line and I find the margin of deviation, whatever, and find the range over 2. I don't know what you said. And I told you it's a good method. This is another method that is more advanced to find the error on the slope. You will end up, for example, with a value like 0.1. So you say my slope is 2.1 unit plus or minus 0.1. Yeah? You still believe this is a bit confusing? And I totally agree with you.
Can you go back to the slide of the presentation?
This one.
Yes. Just in case you misunderstood me, I wasn't asking to explain this equation that is in the red box. It is this
delta
E1 error value that I do not understand from where we got.
All right. So, and probably the same equation is written here, right? Okay.
Yes, this is the one.
Yeah. So what is E? The deviation in the average was basically the actual measurement minus the average. Okay, this is how to find the deviation whenever I have an actual measurement, like one measurement. For example, the mass measured 5 times. But here we're dealing with a 2-dimensional measurement, like we have F versus A. You have different forces and different accelerations, right? And here, to be able to find the deviation, we have to look for vertical deviations, basically. So the method I'm teaching you is only for vertical deviation. So to find how far away this point is, I'm gonna take the ordinate of this point and the value of the straight line. This is the ordinate of the point, and this is the value of the straight line. I'm gonna calculate this one and calculate this one and find the difference. The difference will be how far away the point is from the straight line. And to be honest, the straight line is your average, isn't it? Isn't the blue line the average of all the points? So this is called E1. And this is very similar to D1, to be honest. I'm just showing how this is similar to that. But D1 is 1-dimensional and E1 is 2-dimensional, where you include the slope, the y-intercept, x1 and y1. Did I answer your question, Anthony?
Yes, I understood.
Yeah, I know that probably you got the idea, and I know for a fact that the idea is still very tough on you to understand. I'm gonna revisit this many times, I promise. Meanwhile, if you watch the video on how to calculate the error on the slope, probably things are gonna look a bit more familiar with you, all right? But I promise I'm gonna discuss this even more next time I see you, because you need to train yourself many times for you to be able to learn how to do this, okay? And eventually it's just a mathematical equation to apply, and that's it. All right, and this is where I wanted to ask you to find, didn't we do supposedly here the slope? And in this slide, they want the error on the slope. Let's not do that. Let's do it in lab 3, okay? All right, so now what do we have on our plan? We're done with linear regression, but we need to revisit because this is still somehow blurred to you. Now lab 3, I have a lot of typo mistakes. I'm gonna fix them later. Lab 3, centripetal force, what it is, the theory and the experiment. The theory is not super tough, it's regular. The experiment, the setup is a bit difficult to understand, but since I'm doing the experiment for you and I'm giving you the results, it's not gonna be an obstacle for you. But understanding the experimental setup is very important, and I hope the video is gonna be clear enough for you. Meanwhile, what do you mean, Priscilla? That we have, yeah, we still have lab 3. Do you mind? Let's give it a try. If you believe it's a big deal, we can postpone. But postponing will be bad because the earlier you finish up to lab 4, the better for the midterm. Let's try, okay? However, the lab report is not long. It's a very tiny table and you need to plot. It's a very small lab report compared to lab 1 and 2, okay? So I think let's give it a shot. Before I start, did you do centripetal force in the course or not yet? You did. And even if you did not, it's okay because this is like grade 11 material, but I just wanted to see how fresh it is in your mind. So this is how our presentation would start. Centripetal force. This is the outline. What is acceleration? What is the centripetal and tangential acceleration? How do we use Newton's second law to find the centripetal force? And then our experimental setup and analyzing our data. What are we measuring? What is the variable? What is the constant? And so on, okay? As you can see, the slides are empty, so I want us to do this together. I want somebody to help me define acceleration. How do you define acceleration? Anyone?
Change in velocity over time.
All right, change of velocity over time. I like this. I would want to write the rate at which, because rate has time in it, the rate at which velocity changes, okay? Thank you for stating velocity, because a lot of other students would say speed by mistake, okay? All right, now the question is, how do you define velocity? Anybody? So how do you define velocity?
Change in position over time.
Yes.
The rate at which.
The rate at which the displacement is changing, change in position. Is it a scalar or a vector? Displacement over
Vector.
time, it is a vector. All right. How is it related to speed? Is velocity speed? And if not, what's the difference? It has a direction. Can I say that the velocity is speed and direction?
Yes.
Okay. So when I say that the acceleration is the rate at which the velocity is changing, can I say it's the rate at which the speed is changing and the rate at which the velocity is changing? So if I have a change in speed, I have acceleration. If I have a change in direction, I do have an acceleration. And here, if I need to move on to centripetal and tangential acceleration, when the speed changes, so when the speed is actually changing, I'm gonna call this tangential acceleration. And to be able to find it, I'm gonna take the final speed minus the initial speed over time. Okay, this is simply discussing the magnitude of the speed. But if the direction is changing, I'm gonna call this centripetal acceleration. Some people call it normal acceleration, and I'm gonna explain why. And I cannot do this anymore because assuming the speed is constant, can you remember how to find the centripetal acceleration?
It's V squared over R.
Exactly. So it is V dependent and radius dependent. The smaller the radius you go through to turn your car, the more you feel the centripetal acceleration in your body and you'll be projected outward. And the faster you go, the more acceleration you feel in your body projected outward. And I cannot use this equation anymore for the centripetal force, because assuming the acceleration here is only changing my direction and not my magnitude, which means my magnitude is going to be constant, okay? Now the tangential acceleration, as its name is always tangent to the motion, the job of which is going to speed me up and slow me down. However, the centripetal acceleration is always normal. Normal means perpendicular to my motion, and probably you can see it here, or however this is the force, but you can see the centripetal force or acceleration is always perpendicular to my motion, you see? So that's why in many books they call it the normal acceleration, and it's okay. Centripetal means towards the center of the motion, and normal means perpendicular to my trajectory, and they go hand by hand because the perpendicular to the tangent is centripetal, isn't it? All right, now discussing Newton's second law. What was Newton's second law again? Newton's second law, the famous.
Force is equal.
All right,
Okay.
so net force is equal to ma. I'm gonna assume that my only force here is the centripetal force. So I'm gonna say centripetal force to be equal to ma. I just removed the vectors. I'm gonna replace this by the centripetal acceleration, which is v squared over r. So to find the centripetal force, I will do mv squared over r. All right. Remember, there's no force called the centripetal force. Usually when you have a system, you're gonna have many forces on that system, the resultant of which could be tangential or could be centripetal to the motion. If it's tangential, it's gonna speed you up or slow you down. If it's centripetal, it's gonna help you turn in a circle. Sometimes it's neither tangential, neither centripetal, which means it has two components, one component to speed you up and one component to slow you down. So there's nothing in nature and real life that's called centripetal force. Tension in a wire could be centripetal force. Force of gravity could be centripetal force. So centripetal force is the net force you have on your system. I don't know if these examples will help us out. This is a satellite orbiting planet Earth. The only force on the satellite is the force of gravity, and you can see for a fact that the gravitational force is centripetal. Wherever the satellite is, the force is directed towards the center. That's why I have a circular motion. And by the way, centripetal force will not slow down, neither speed up the object. Hence, you will have a uniform circular motion. Here, the girl is spinning a ball on a string. So the centripetal force here is the actual tension, right? Here you have a car turning. The centripetal force, actually, you have some friction. Otherwise, the car is gonna slide outward. So you have normal force, force of gravity, and some frictional force to help up with the rotation. And here you have a roller coaster, and you can see that you have the normal, the force of gravity, and this would help you go into a certain rotation. So the net force is the centripetal force. And this is the same example as the satellite motion, all right? This is just to show you that centripetal force is everywhere. It's not one particular force. It could be many things at the same time. By the way, if the road is not straight, horizontal, the normal and the force of gravity in this case will not cancel out. You will have some mg sin theta, and it will go along with the friction to help you with the rotation. All right? Anyway, I don't need us to discuss a lot of that unless you have questions. Let's discuss our setup, because our setup is complicated enough. Why study all the different examples? This is our setup, okay? Let me start with the actual diagram. So what do we have? You start, this is the apparatus. I'm gonna call it a stand. You have a rotating platform. This is like a ruler that would rotate horizontally, clockwise or counterclockwise. The rotation is so smooth. The friction is so low. You would love playing with this. You have a central post that I'm gonna center in the middle. And you have a slide post. I'm gonna move the slide post. This is my system. Keep that in mind. So this is your system. The system that will undergo rotation, the system of which I'm interested in the velocity and the mass and so on. Don't be confused, because a lot of students would think this is the system. No, the system is this one. I usually call it the yellow mass. It is yellow in this experiment. Probably here in the picture you can see it's yellow. Before you start the experiment, you have to create an equilibrium. By the way, please ignore those. In our case, we did not have any extra mass. How do we set our system? You're supposed to attach the yellow system with a wire. Please listen up very carefully. Wire in here, and wire in here, and wire in here through a hanging mass. Definitely when you have attached a wire and a mass, this will be centered exactly like this one. Let me remove the mass. You will see that your yellow system will go a bit to the right, obviously, because nothing is pulling it to the left. Okay? Now what happens here? You have something very interesting. This wire is around a very smooth pulley attached to a red ring, and then you have a spring in here. Okay? Let me remove the green annotation. Your job is to move the white ring close to the red ring, because you need to remember where the red ring is. Okay? So let me show you again. When you attach the hanging mass in here, all right, you will have the red ring and the white ring at the same level. When you remove the hanging mass, automatically your yellow object will go slightly to the right and the red ring will go a bit up. It will be deviated from the white ring, and that's okay. Then you will remove the pulley just for your platform to be symmetrical, and you will start the rotation. With your hand, you're gonna kick the rotating platform to rotate clockwise or counterclockwise, it doesn't matter. What happens to your yellow system? It's gonna move outward due to the inertia. You know, when something is rotating, due to inertia and due to the fact that the motion is centripetal, the body will be projected outward. So your system is probably gonna go back to its initial position, and the red ring is gonna go back to the white position to mimic a centripetal force equivalent to the weight of the hanging mass. So let me say it again. You attach a hanging mass. Let's say the mass of which is 10 grams. Let's assume gravity is 10 meters per second squared. Grab a calculator. 10 grams divided by 1000 to change it to kilograms multiplied by 9.8. Let's not assume gravity is 10. I'm gonna get 0.098 newtons. So I just created 0.098 newtons on my system. I fix my system to create equilibrium and make sure the red is on the white and so on. I remove the mass and I remove my pulley, and I'm gonna create rotations to be able to mimic the 0.098 newtons. So the rotation will mimic a force equivalent to the initial hanging weight. How do I know I'm mimicking the exact same force? It is when the red ring will go back to its initial position. This very simple idea is very confusing for the students. Okay? Now let me try, and probably you understood the whole thing, but not really well. Let me try to open the video to show you things, because probably when you see it, it's gonna be easier for you. This is the video. And again, my videos are tiny in size. I mean in actual size. This is the platform. I'm explaining here. All right, let me see. Do you have a pulley? All right. So basically you do have a pulley and you do have a hanging mass. This is the yellow object. It's copper or something yellowish. I think it's copper. It's attached by a very thin wire, and you have 3 hooks, one of which will go to the pulley, one of which will go to the sliding post, and one of which will go to the red ring, okay? I'm gonna make everything central. Let me start. Central post on which you have a spring with an indicator, and here you have a pulley. You have a sliding post where you have your mass. This is 200 grams. This is your system, by the way. Focus on the motion of your system. And your system is actually connected to 2 wires, 3 wires to be honest. 1 wire which is connected. All right, let's move this a bit. Probably I can show you the horizontal and vertical lines. You need to make sure your system is ready for the experiment before you start taking measurements. All right, let me move a bit closer to show you how I'll be doing the connections. All right, first of all, I want to make sure that there is a wire connected from my spring to the system. Then making sure the system is connected to the sliding post. All right, so I'm taking a lot of time explaining this because I want you to understand. Let me see the section where I move my black indicator. Okay, here I'm showing you that this is well vertical, this is well horizontal, and this is what I want before I start the experiment. And then I want to move the black, okay, here. Mass is not moving because as long as the hanging mass is moving, the spring would be moving. So I'm gonna move my black post in such a way to make it aligned with the orange indicator. What? All right, so the black post is only to remind me where the orange indicator was, because when I remove the hanging mass, I'm gonna lose track of the position of the orange indicator. It's gonna move up, you see? So, and now I'm gonna remove the hanging mass and the pulley. I'm doing this because I'm gonna start the motion. Okay, let me fast forward. I remove the pulley and the hanging mass, and now I'm gonna create rotation. Okay, so you see the orange moved up a bit, not a lot because the hanging mass was very light. I will do the experiment again with heavier masses. Okay, if I move so fast, okay, this is nice to see. My orange indicator on the black level, all right? So you can see that I shouldn't go too fast, neither too slow to have this equilibrium. Meanwhile, your partner... Okay, all right. So if I move too fast, the yellow will go to the left and the wire will pull the orange indicator down. I don't want this. If I move too slow, the yellow will not move far enough. So the orange indicator will be above the black. So I need to find a speed with my hand that would give me a centripetal force, a rotation that would give me the centripetal force equal, and put the orange indicator exactly at the black position, you see? Just to mimic the same force given by the initial hanging mass. All right, now let's take a tiny break to show you what values you're supposed to do. You have to pick a radius for your system, and you can simply move this post right and left at 5 centimeters at a time to increase the radius of your system. The radius is the distance between my system and the center of the motion. Period is the time taken to complete one rotation. The period is important. Why? Because it helps me find the velocity of my system. Remember, speed is distance over time. If the time is taken to be 1 period, the distance covered will be 1 full cycle, and 1 full cycle is 2 pi r, the circumference of 1 cycle. Knowing the radius and the period, you can find the velocity, right? By the way, it's very difficult to measure 1 period or the time taken to do 1 cycle. Probably you grab your stopwatch, it's gonna be your smartphone, and all smartphones will give you 2 decimals as a digital measuring tool. Keep that in mind, check your smartphone. So you're gonna measure the time taken to do 5 rotations, and then you divide by 5. All right, read the procedure and see. And then you're gonna do t squared because plotting r versus t will not give you a linear relationship. Now let me remind you, we had f to be equal mv squared over r, right? mv squared over r. F is a constant because it's equal to the hanging mass, and I'm not gonna change the hanging mass. I'm gonna change the r, and I'm gonna change the speed. to get a linear relationship. So probably I can, what do they want me to plot? Radius versus square of period. Let me write the equation again in terms of r. So it's going to be r equals mv squared over f, right? Be careful, m is the mass of my system, the yellow system. And the centripetal force is the weight of the hanging mass, which is mg, and m is a different system. Okay, so here you have small mg of the hanging mass, and I'm gonna call this big M of my system. Now V would be replaced by this guy. Eventually you're gonna have R as a function of t squared. If you replace V by 2 pi r over t and make sure you square the whole thing and write the equation again as r as a function of t squared, you will obviously get a straight line passing through the origin. Your job is to draw the best fit line, easy Excel. So plot means show the points. Draw the best fit line, show the equation of the line, and add the trend line. Measure the slope of the line along with the error on it. The slope, you can read it from the equation of the slope. So item 3.4 can be done in one click on Excel. Now the error on the slope will take you some time. Try to do it. If you cannot do it, next time I see you, we can sit together and take our time on it. Then they want you to deduce from the slope. In other words, what does the slope represent? Is it m times 2 pi? Is it m times 4 pi squared? Is it m divided by 4 pi squared? Write the equation well, you can tell. And from your slope, deduce the centripetal force. And then find the error on it. Obviously, you knowing the error on the slope, you can find the error on the centripetal force through propagation of error. And then they want you to compare. Compare means find the percentage difference. List the sources of errors. And that's it for the lab report. You see, you have to do a plot to give the equation, error on the slope, find the centripetal force from the slope, and the error on the centripetal force. Then compare sources of errors. I know this is tough, but this is all you need to do. And you only have 5 values to play with. And the values will be given by me. Okay, can we give it a shot? Let me show you the lab reports. Where is my manual? This is the manual. This is lab 2. Supposedly lab 3 is afterwards. Give me a second. Are you still there? Did you die? Did I lose you? Okay. Jane and Priscilla are still here. Eli is dying. All right, so you see the lab report is only 1 page. Okay, calculate the weight, fill the data. I will do it for you. Probably all you need to do is add t squared. That's it. And these are the questions. All right, and this is a very tiny conceptual question that is not difficult to do. All right, so I want us to try this on. So next week will be your week to play around with Excel, how to plot the equation of the straight line. Eli, let me be your partner if you need help. Let's break it down. Do your lab report. Do half of it alone and half of it with me. I think it's gonna be okay. I'm gonna save as this presentation so I can keep a copy for you. By the way, can you see the edit? Can you see those lines?
Yes.
Okay. Yeah,
Yes,
I
yes,
don't
we can.
understand like, why my other students cannot see them. Anyway, if you can see them, that's great. All right. So next time I see you, obviously the lab report is going to be due Monday evening, which means next time I see you, we can take time to go over it again if you need us to. All right. Cool. That's it for today. Thank you so much. Remember, you're gonna take your time to watch the video. Probably if you watch the video, things are gonna get easier. When you get the results, things are gonna get easier. I can also give you a hint. How about you read the procedure? The procedure tells you what to do, and the video shows you what I'm doing. And now I just explained what I did. So you have 3 different procedures, one written, one that just happened now by me, and one where you have it in a YouTube video. Probably it's gonna help you understand. Worst case scenario, you don't understand the experiment or you understand part of it. Remember, you have the results. The mathematical part has nothing to do with the experiment. So all these ideas and skills are not very tightly related. So you're not gonna end up in big chaos, okay? All right, so that's it for today. You can leave if you want, you can stay if you have questions, or you can take a few hours off to think about it and ask me again. Thank you. Somebody has a question?